Pleasant. Let's talk about the universe. Verse. Yes. We're about to talk about the universe. Verse. We are going to do cosmology. And we're going to write down the Robertson-Walker metric. We're going to write down the Friedmann equation. We're going to see how all that works. It's remarkable. If you assume that the universe is homogeneous, the same everywhere from place to place, and isotropic, the same in every direction, the equations describing the overall evolution of the universe are remarkably simple. So we'll talk about that. First, we'll start with Newtonian cosmology, which of course isn't right. So we're going to treat gravity in the Newtonian way and come up with a Newtonian version of what we call the Friedmann equation. And then we get out some chicken feet, wave them a little bit, and say, here's what happens in GR, and then kind of go from there. So even though what we're doing right now to start with isn't accurate, I think it's still motivating to get intuition sort of into what's going on. So we will start with Newtonian cosmology. And so what I want you to imagine is that we've got this sphere that's of uniform density, and for whatever reason, it's either growing or shrinking under its own gravity. If it's growing, its gravity is going to be slowing its expansion down. If it's shrinking, its gravity is going to be speeding it up. And then you imagine kind of extending this to infinity, if you will, to think about an expanding or contracting universe. But for now, let's just talk about a sphere whose radius is capital R sub s, radius of the sphere as a function of time. It's got constant mass m sub s, the mass of the sphere, because it's just growing or shrinking, and the mass inside of it is just going along with it. And I put an adorable, and I'll also say it's got some density as a function of time, which we again assume to be uniform. It's the same everywhere, so I'm just write a single number that its density is a function of time. And we have here a cute, adorable little test mass, if you will. So just one particle on the surface of the sphere that is going to feel the gravity and accelerate, and then, Newtonian physics, Einsteinian physics, the acceleration is independent of mass, so it's going to drop out. But there's our little test mass. So, just to summarize, we have a sphere of mass m sub s and radius r sub s that is of uniform density. It's the same everywhere. Uniform density. And it's expanding or contracting under the influence of its own gravity. That's our scenario. It's the only thing around. It's the whole universe. What happens next, shall we say? what's the force on my test mass? Well, I've got, it's being pulled on by a uniform sphere of radius r sub s, mass m sub s. What's Newton's law of gravity says is going to be the force of gravity on that cute little test mass.
And time ms times n over r squared.
Yeah. Times one more thing.
And g.
Yeah, big G. Right, yep. So the force is minus G, capital MS, cute little m, over r sub s, which will be a function of time squared. The minus sign just says the force is towards the center. That is going to make the center, basically. And since that's true for every little mass on the surface of the sphere, everything around, then we know what the acceleration of the surface of the sphere is. Just divide through by little m, the acceleration of the surface of the sphere, the acceleration due to gravity on the sphere's surface is minus gm sub s over r s of t squared. But the acceleration of the surface is just d squared rs dt squared, right? Because that's what acceleration is. We have to change of position. So we can say that d squared r sub s dt squared, second derivative of rs, is equal to minus g times m sub s over rs as a function of time squared. What questions do you have at this point? So now, note that m sub s is density times volume, right? It's uniform density. So mass is density times volume. What's the volume of our sphere? Like any self-respecting sphere that's in flat space, actually. What's its volume?
4/3 pi rs cubed.
Yeah, 4/3 pi r cubed is its volume. Yep. So that'll be then that it's its density times its volume, which will just be 4/3 pi rho as a function of time, rs as a function of time cubed. That's a constant, right? And the mass of the sphere is a constant. But for arbitrary radius inside the sphere, the same is true within any spherical volume centered on its center. The same thing is true. The mass of that volume is the same relation. So we can say that m sub r, the mass interior to radius r, like we met when we were talking about stars, m sub r mass inside radius r is 4/3 pi rho of t r of t cubed, because as the sphere expands or contracts, all the spheres inside of it that contain a certain amount of mass are also growing or shrinking. we got that same relation. And so if I'm at some r within the sphere, there's RT, which is less than the radius of the sphere. If I wanted the force of gravity on a test mass on its surface, does the gravity interior to its radius contribute? Does the mass interior to its radius produce gravity on it? Yes. Does the mass outside of its radius produce a gravitational force on it? No. It's just like with the electric field. The gravitational field is an inverse square law force. Gauss's law holds for the gravitational field. We've talked about this before. Only the mass interior to radius r contributes a gravitational force on the test mass. So this equation actually holds for every radius inside the sphere. Any arbitrary radius inside the sphere, since only m sub r, the mass interior to radius r, contributes a net gravitational force, we can write that same relation anywhere inside the sphere. We can say that d squared r dt squared is equal to minus g m sub r of t over r of t squared. Same way. No, that's not a function. M sub r is not a function of t because the mass interior to a given radius stays inside it as it either grows or shrinks. So m sub r is a constant still. But m sub r is 4/3 pi rho r cubed. And so when I divide by r squared, that just turns into minus 4/3 pi times, just put that in there, 4/3 pi g rho of t times r of t. And what this means is that the acceleration within the sphere is at all times proportional to how far you are from the center. If you're twice as far from the center, the acceleration is twice as large because rho is, at any given moment, rho is the same everywhere inside the sphere, g 4/3 and pi, those are all constants. So the radius of the sphere at any given moment is the thing that determines what your acceleration is. And the further are you away from the center, it's proportional to it, the greater the acceleration. So acceleration is proportional to r. Acceleration is proportional to r. So if the system is let go from rest, pausing to let you catch up. So if I build this sphere and everything initially is at rest, and then, so somehow magically holding everything in place, and then I just let everything go, what's it going to do? It's going to start shrinking, right? Because gravity's pulling everything in. And, okay, so I let everything go from rest. And let's say that this is half the radius of the sphere. Compare the acceleration at half the radius of the sphere to the acceleration at the surface of the sphere. How do they compare? How does this acceleration compare to this acceleration?
Squared and second, that's it.
Well, the acceleration, d squared r dt squared at any radius, is stuff, right, times the radius, right? So if this is half as large as the surface value of r, the acceleration here is at that moment how big compared to the surface acceleration? Half as big, yeah. If I'm 1/3 of the way out to the surface, the acceleration at that location compares how to the acceleration at the surface? 1/3 as big, right? Wherever you are, whatever fraction of the way you are to the surface, your acceleration is that fraction of the surface's acceleration. So, and that's true at all times. So everything's acceleration is increasing because the gravity is getting stronger and stronger everywhere. The acceleration is increasing, but it's always true that points which are, say, halfway to the surface always have half the acceleration of the surface. And that means that at all times, since I've let everything go from rest, these points that started out halfway to the surface are always moving half as fast as the points on the surface are. So as everything collapses, like suppose this is the center, and here I got 2 points, surface, halfway to the surface. This point is always moving half the speed of this point at the surface. And what that means is, well, let's see, how far do they have to go? Well, this one, to get to the center, this one only has half as far to go as the point at the surface. So what happens is, if you let it go from rest, everything will reach the center at exactly the same time. Because it's always true that something twice as far away is always moving twice as fast. It'll cover twice the distance in exactly the same amount of time. So everything will collapse, will reach the center at the same moment. If the system is released from rest, this means that velocity v is also proportional to r. So every point in the sphere will hit the center at the same time. Every point in the sphere will reach the center at the same time. This is what we call, and we met it when we were talking about star formation. One of the problems talked about this. This is called homologous collapse. What a great word. Homologous collapse. How are you feeling today? I'm feeling homologous, thank you. I don't know what that means, but I mean, you know what it means to feel homologous. I feel like I'm going to collapse to my center all at the same time today. Maybe that's not a good thing. Homologous collapse. So run this backwards, right? I release them for rest, everything is centered at the same time. Run the clock backwards. Everything's expanding away from the center, right? And getting more and more spread out. And somebody at the center sees something twice as far away, moving twice as fast. One can convince yourself that would be true everywhere in the sphere. Something twice as far away is getting further away from you twice as fast. Does that remind you of anything? What does that remind you of? Why, do you know of anything that is expanding, that we think if you ran the clock backwards, everything was concentrated all together? Everything is a universe. This reminds us of the universe, the idea of the Big Bang, right? So this is why we're doing this. It is quite analogous to the idea of the Big Bang. You can make the sphere of arbitrary radius, make it as big as you like. So it's the universe everywhere. And you run the clock backwards, and everything used to be all infinitely concentrated together. You run the clock forwards, everything is spreading apart, spreading apart, spreading apart. That's the point of all this. Oh, Big Bang, anyone? Big Bang, anyone? The correct answer, of course, is yes, please. Okay. Questions, comments, observations? Run it backwards, and it's a homologous expansion. And back before we knew about dark energy, that's what we would expect for the universe, is that it's expanding, but it's slowing down, if you were. And the Newtonian point of view would be the gravity of the galaxies pulling on one another is slowing down the expansion. So, next up, we're going to do something which you've probably seen before. This is actually directly analogous to how you prove the work energy theorem in first year mechanics, or just mechanics in general. Let's do that. What I'm going to do is multiply both sides of this equation by drs dt. So this is the acceleration. We're going to multiply both sides by the velocity. And then we're going to recognize stop. Multiply by drs dt. Right, that's how fast the surface is moving. And again, you do this at any interior radius. The math works out the same everywhere inside the sphere. Multiply by drs dt. I'm leaving that there for the moment, so we can continue to see it. So that says d squared rs dt squared times drs dt. First, you're like, okay, how are you doing, right? Making it more complicated because that's a derivative. Is equal to minus g m sub s over r sub s of t squared times dr sub s dt. But if I have d squared rs dt squared times drs dt, that's the same thing as 1/2 of ddt of drs dt squared. Because what's the derivative of drs dt squared? From the chain rule, what's the derivative of drs dt, the quantity squared? It's that, obviously, but in the end, when I multiply both, yeah, ddt of drs dt squared, right? is going to be what? How would I do that? Well, if this was just u, and I wanted ddt of u squared, if I just call u drs dt, what's the time derivative of u squared according to the chain rule? 2u du dt, right? It's 2u du dt is the derivative of u squared, right? Because it's the derivative of u squared with respect to u times the derivative of u with respect to t. We'll now apply that to drs dt being u. Then this says that this is going to be that the ddt of drs dt, the quantity squared, will be, just make the substitutions, 2 times drs dt times the derivative of drs dt, which is the second derivative of drs dt. Right? Direct application of just letting u be drs dt. And so ddt of the quantity of ddt of drs dt squared is equal to 2 times drs dt times d squared rs dt squared. So when I multiply by 1/2 to cancel the 2, these two things are the same. They're equal to one another. And over on the right-hand side, we can recognize that as being the derivative of gm over r. This is the time derivative of g times the mass of the sphere over the radius of the sphere. Because here we're saying we've got ddt of rs to the minus 1. What's ddt of the radius of the sphere to the minus 1 power, because it's over in the denominator. What's ddt of rs to the minus 1? Chain rule says?
Negative rs times dt rs.
So rs to the minus 1
Minus 2 to minus
to 2, right? So it's going to be minus rs to the minus 2, right? Minus 1 rs to the minus 2 times
drs dt.
times drs dt, because we've got to apply the chain rule, got to differentiate the inner function. Right? So indeed, GMS is just hanging out because they're constants. The derivative of 1 over rs is in fact minus 1 over rs squared times drs dt, right? Because rs to the minus 2 means same thing as minus 1 over rs squared drs dt. So this is why we did this, because now both sides are derivatives, time derivatives of something. If both sides are time derivatives of something, why, how do I undo a derivative? 2, 4, 6, 8. It's now time to integrate. And boy, is it ever going to be great! Great! We're integrating. It's going to be great! 2, 4, 6, 8. It's now time to integrate. Boy, is it ever going to be great! Great! Yes! All right? Feel like Tony the Tiger. It's great! Right? Okay? So, we integrate both sides to undo those differentiations. And integrate! We just want to show how happy we are here. So, if I integrate ddt of the quantity drs dt squared, what do I get? Integrate with respect to time. What's the integral of the derivative of drs dt squared?
drs dt.
It's just drs dt squared plus constant, right? And if I integrate the derivative of gm over r, why that's
G over
gm over r plus
constant.
a a constant. We'll just put the two constants together, the two integration constants together, and we'll say we get that 1/2 drs dt squared plus equals gm over rs as a function of time plus u, constant of integration, why this is so important. This has become equation 1 circle. It's equation 1. We can refer back to it later. And here's the thing. So, yes? It is, thank you, yes. Just being sure you're paying attention. Congratulations, you're paying attention. Yeah, definitely catalyze this, yes. So this is half times the velocity of the surface squared. 1/2 v squared. Gosh, 1/2 v squared. What could I use to maybe turn that into some kind of energy? So 1/2 v squared, like, 1/2 v squared is almost an energy. What do I get if I'm moving along at speed v here, 1/2 v squared, what do I need to multiply to make that? Yeah, 1/2 mv squared is kinetic energy, right? So this is the kinetic energy per unit mass. Kinetic energy per unit mass. If we had our little test mass m, 1/2 m v squared would be its kinetic energy. Divide by its mass, you get 1/2 v squared. This is the kinetic energy per unit mass of any particle at the surface. KE per unit mass. What's that? What's GM over R? Kind of, well, the gravitational force is minus GM over R squared. But what's the thing that's minus GM over R instead of R squared? Instead of the force, it's the potential, well, yes, GMM over R squared is the force, right? And so minus GMM, the minus sign of the plus sign of the force, which are, so, okay, minus GMM over R squared is the force. Minus GM over R, GMM over R is the gravitational potential energy, right? And if we divide through the by the mass, it's the gravitational potential, or in other words, the gravitational potential energy per unit mass, with a minus sign, just it has a plus sign, and the gravitational PE has a minus sign in it. So this is minus the physical potential energy per unit mass. Gravitational potential energy minus PE per unit mass. So this equation represents conservation of energy. It's just conservation of energy. Oh, yeah, it's D. And now, we're going to start introducing relevant cosmological concepts, the first of which will be what we call the scale factor, which in cosmology essentially represents how big is the universe now compared to how big it was in the past, how big it will be in the future. And by that I mean that what we do is we end up saying the scale factor is 1 today. And in the past, when the scale factor was, say, 1/2, everything was half as far apart as it is now. And when the scale factor is 2 someday, everything will be twice as far apart as it is now. So in some sense, that's how much the universe is bigger or smaller. Now, if the universe is infinite, what does that mean? Well, it really means how far apart are things now, or at some other time, compared to how far apart they are now. So, m sub s stays constant as the sphere expands or contracts. Oh no, we already said that earlier, so I don't need that quite right now. So, we're going to write that the radius of the sphere as a function of time, we're going to say that's equal to a as a function of time times little r sub s. A of t is the scale factor and we will note that r sub s of t is equal to r sub s when a of t is equal to 1. So little r sub s represents the radius of the sphere when the scale factor is equal to 1. And because it's the radius of the sphere when the scale factor is equal to 1, we've specified that it doesn't change with time. As the sphere expands, say it's expanding because the universe is expanding, it could also be contracting. As the sphere expands, little r sub s for the surface stays the same because it's defined to be the value of the sphere's radius when the scale factor is 1. It doesn't matter what the scale factor is in the future, little r sub s is defined to be the value when the scale factor is 1. So, r sub s is what we call the co-moving coordinate of the surface. Really, it's the co-moving radial coordinate of the surface, r coordinate of the surface, which stays constant as the sphere expands or contracts. So it's kind of like we've got this coordinate system that's growing or shrinking with the sphere itself. The radial coordinate just grows or shrinks with the sphere itself. The value of rs at any point within the sphere, as the sphere expands, that keeps going with it so that rs stays absolutely the same for every point within the sphere, which stays constant as the sphere expands or contracts. Very crucial concept, because we're going to do that with the universe too. Questions? Got the picture? I feel like you don't got the picture. You're not happy with something.
No, I think I got it.
Yeah. So in other words, let's make it, let's say this is, I don't know, well, what if it was a meter, okay? 1 meter. So here, radius of the sphere is 1 meter, and let's say this is when we're just defining, and you get to choose when the scale factor is 1. So what we do with the universe is we say the scale factor is 1 today. If we were born 7 billion years ago, we would define the scale factor to be 7 billion years ago. You pick any time to be the time when the scale factor is 1. Later on, scale factor's 2. So what's the radius of the sphere when the scale factor's 2? 2 meters. What's R sub s at that time?
1.
It's still 1 meter because it doesn't change, which note is A of t times, and then we'll note that R sub s, right, is A of t times little r sub s. So here that's going to be A of t is 2 times 1 meter equals 2 meters. Right, so R sub s stays constant, multiplied by the scale factor, and that's the actual radius of the sphere that moves. That's the idea. Okay. And you can do that anywhere inside the sphere. Every distance, every co-moving coordinate value has to be multiplied by the square factor, by the scale factor to turn it into an actual distance. Okay? So, now, check this out. So we've got that Rs is equal to A times little rs. So it's understood that A is a function of time, big R sub s is a function of time, little r sub s is the co-moving coordinate space constant. All right? Now, you all familiar with dot meaning d dt? If I put a dot over a quantity, it means its time derivative. So let's take the time derivative of both sides here. Rs dot is equal to, now in general, it would be A dot Rs plus ARS dot using the product rule. But what's Rs dot? 0, because it's constant. Little r sub s is constant. So big R sub s dot is A dot times little r sub s. In terms of which, the energy equation, 1, becomes 1/2 Rs squared, A dot squared, in other words, 1/2 capital Rs dot squared, 1/2 drs dt quantity squared. So capital Rs dot squared is little rs squared, A dot squared, is equal to, now we had that, we're going to say it's gm of the sphere over r sub s, but again, the mass of the sphere is going to be 4/3 pi rho r cubed, so we can write as 4/3 pi rho g rs cubed over rs. So this just turns into 4/3 pi rho g rs squared for gms over r. Rs squared is A squared little rs squared. So if I say rs without decorating it, that's the big R, and if I say little rs, that's the little r. Try to keep to that for now. So this is equal to 4/3 pi g little rs squared rho of t, I'll just say rho, it's understood that's a function of time, rho times A squared plus u, because u is that integration constant. Now, we're going to multiply by 2 over rs squared a squared on both sides. And that's going to give us, so I'm going to get a dot squared over a squared. That's going to give us a dot over a quantity squared. And so the 2 over rs squared is going to cancel this half rs squared. So I just get a dot over a, the quantity squared, is equal to 8 pi g over 3 times the density as a function of time. I'll go ahead and note again that the density depends on time, plus 2u over r little rs squared times 1 over a of t squared. And I'm going to draw a box around this equation because this is the famous Friedmann equation in Newtonian form. And then after the break, we'll say, and in general relativity, I wave some chicken feet and it becomes this other thing that looks similar but not quite the same. That involves the curvature of the universe. Friedmann equation in Newtonian form. So I should have pointed out at the beginning, there's a book, Introduction to Cosmology by Barbara Ryden down at Ohio State, which is fan-friggin-tastic. It's an absolutely wonderful book. And my notes for this part are based on it. And she's hilarious. Like, she gives advice like, you should write the Friedmann equation on your forehead backwards so that you'll see it every morning in the mirror while you're taking the course. So feel free to follow that advice. This isn't quite it yet. You can put the GR version of it. But.
Don't write that one on the forehead.
What's that?
Don't write that one on the forehead.
Don't write this one on your forehead. No, wait for the one that we say, well, here's what happens.
That's why I just don't want the forehead.
Yeah, because that we don't want you to, I don't know. That's kind of awkward, right? Because then you're like, now I gotta get my tattoo removed. Oh, never get a tattoo on your forehead. Okay, let's do it. Take a break. Yeah, so intuitively, right, you got the sphere expanding. If everything was moving fast enough, why maybe it's at every point is past its local escape velocity, and it would just expand forever. But if it's not expanding fast enough, eventually gravity stops it, and it falls back together again. And if it's moving at just the right speed everywhere, it expands forever, and in the limit of infinite time, it stops expanding, right? So this is analogous to, in principle, you throw a ball upwards, no atmosphere, throw it past escape velocity, it flies away, and even infinitely far away, it's still moving. If it's right at escape velocity, its velocity approaches zero, infinitely far away. If it's below escape velocity, it finally stops and falls back down again. Well, the universe can kind of do that too in this model, and even in GR, dark energy complicates things, but all there was gravity. Had a similar situation where the universe could expand forever, ever, ever, ever. Or expand forever, but stop expanding in the limit of infinite time. Or, oh my God, Anushka, what are you doing?
I'm so sorry to interrupt, but my thirst for knowledge compels me to come closer to the board.
Oh my, that's wonderful. I forgive you. Please do.
Thank you so much.
All right, very good. Okay, so, or the universe could be not expanding fast enough, and it eventually stops expanding, falls back together again, and so the Big Bang is followed by the Big Crunch, or as I prefer, the Big Bang spelled backwards. There are analogies in the Einsteinian general relativity version. Let's just do the Newtonian version first. It's going to be controlled by this potential energy term right here. Potential energy term per unit mass. Why, let's list the possibilities, shall we?
Yes, we shall.
Yes, we shall. Yes, I was waiting. That's something somebody with a thirst for knowledge would say right there.
Absolutely.
You know it. Alrighty. So, first of all, note that A dot over A squared appears. So the idea there is that that could be either positive or negative. And because of the fact that it's either plus or minus the square root of all that stuff there, contraction is just the time reversal of expansion. Right? You just run the clock forwards or backwards. So A dot, I'll put it like this, I'll put it like I do in the notes. A dot and A only appear as squares. A dot and A only appear as squares. So contraction A dot less than 0, right, the scale factor is decreasing. It's just the time reversal of expansion, which would be A dot greater than 0. What's the universe actually doing? Expanding or contracting? Expanding. So we'll just, for the most part, we'll concentrate on expansion because that's what the actual universe is doing. But you can just do everything backwards and have contraction too. That would also be a perfectly legitimate solution. Focus on expansion. If u is greater than 0, well, 4/3 pi gr squared rho a squared. Could that be negative? Could 4/3 pi g, could, nobody called me on that. 4/3 pi, oh my god. 4/3 pi grs squared rho a squared. Could any of those terms be negative? No. Right. So if u is positive, the whole right side is positive, right? And so in that situation, things are expanding, A dot's always going to stay positive. So the universe will expand forever in that situation. If u is greater than 0, RHS, the right-hand side, is always positive. So that says A dot stays greater than 0 at all times. Again, if it's greater than 0 at some moment, it stays greater than 0. We're focusing on expansion here. Expansion forever, ever, 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 ever. Ever, ever. If u is less than 0, then A dot starts out positive, because we're assuming that. We assume initial expansion to conform to our universe as it is. But there's going to be a maximum value of A because eventually the right-hand side is going to equal 0. But there's a maximum value of A when A dot is equal to 0, because of course, how do you find the maximum of a function? You said its derivative equal to 0, right? So, but there's a maximum value of A when A dot equals 0. And the easiest way to get it is to go back to equation 1 rather than what we have there. What we do is we say Gm sub s over R sub s, which is the same as Gm sub s over scale factor times little r sub s is equal to minus u. At that point, the right-hand side will be 0, because this is just the second term written as we had it before, Gm over R. So we're setting Rs dot equals 0 in 1 to get that condition, that the right-hand side goes to 0, and the right-hand side was this plus this, set that to 0. And so that says, solve that for A, that gives you A max, the biggest the universe ever gets. Or really, strictly speaking, the largest value the scale factor ever has. So A max is equal to minus G m sub s over u times r sub s. And you might say, wait, does this mean that A max is negative? No, because of the gravitational, because u is less than 0. Potential energy we're assuming over here is less than 0. So A max is greater than 0, since u here is less than 0. And then finally, if u is equal to 0, everything's moving at exactly escape velocity, so to speak. If u is equal to 0, well then, A dot goes to 0 as t goes to infinity, because in the equation I just erased, that would be the densities going to 0. In equation 1, as we wrote it, that would be that the denominator r sub s is going to 0. And so, in that case, the universe expands forever, but in the limit of infinite time, it stops. The limit of the scale factor derivative is a 0 as time goes to infinity. What questions do you have? So there would be an analogous situation in GR, in the real situation, if there were no dark energy, if all we had was matter, and regular energy, so to speak, with no dark energy, we would have an analogous situation before dark energy was found back in the late 90s. That's what we assumed would describe the behavior of the universe, except we have to put in GR. So time to wave those chicken feet. Right, so I've got to put in those waving chicken feet. And next to the waving chicken feet, hi everyone, we say, the correct Friedmann equation obtained using general relativity is, this is the one you're going to put on your forehead. very similar. It's A dot over A, the quantity squared, is equal to 8 pi g over 3c squared times epsilon of t, instead of, so we replaced rho of t with epsilon of t over c squared. And we'll see that epsilon is the energy density, the energy per unit volume, minus, and in place of that potential energy term, we get minus kappa. So I'll point out, that's not a K, it's a Greek small letter kappa, which kind of looks like that. Kappa c squared over r naught squared, the radius of curvature of the universe squared, times 1 over a of t squared. So this gives a box. And this is equation 2. This is the one right backward on forehead. So just see it every morning here. Of course, Dr. Harmon, what do those terms mean that we've put in here? Well, I haven't said it explicitly, but this is for a universe that is homogeneous and isotropic. So the universe needs to be the same from place to place and look the same in every direction. So in other words, we assume that this energy density is the same at every point in the universe. Is the actual universe such that the energy density is the same everywhere?
No.
No, right? If it were, we wouldn't be having this conversation. It would just be this, featureless blob. So, of course, it's an approximation. You have to, as long as you average over volumes a few 100 million light years across, we're good to go here. But the universe is much larger than 100 million light years or whatever, so this is true overall. And this is a simplification where we just assume the universe is just of uniform density everywhere. This would give the overall picture. And we'll say, this is plausible, because look at this piece. So when I say that epsilon of t is the energy density, I mean the energy per unit volume, and that's going to be, for all the particles, they're relativistic energies, right? In other words, their mass energy, plus their kinetic energy, plus potential energy. So mass energy counts as well as this too. Right? So even if you had a bunch of particles at rest, there'd still be energy mc squared associated with them. So epsilon of t is the energy density. Energy per unit volume. Plausible that this should show up. Since for non-relativistic particles, whose energy is almost all contained in their rest mass energy, I shouldn't say their rest energy, I shouldn't say rest mass, I don't like that term, it's just mass. Since for non-relativistic particles, epsilon would just be the mass density times c squared. Heat them up, make them really hot especially, and you start getting a significant contribution from their kinetic energies. So in other words, for non-relativistic particles, this is just rho c squared. divided by c squared. You just get rho, and you're back to the equation we had before. But our equation is still valid if the particles are non-relativistic. It's valid in the general case. And here's where the fun begins. Now for the fun part. And I mean, I'm serious. This is kind of, I love this kind of stuff. Kappa is the curvature constant. It describes the overall shape of the universe, because the universe can have a shape. For a homogeneous isotropic universe. I think homogeneous is a 25-cent word, and isotropics are $1 word, in my opinion. Right, like 25-cent word is one that's kind of fancy. $1 word is one that's very fancy, right? How often does one use isotropic in everyday conversation? Answer: almost never, unless you're a cosmologist, in which case it's a considerable fraction of the words that you say. For a homogeneous isotropic universe, the universe can have one of three possible shapes. You prove this from GR. Namely, it can be flat, it can be a sphere, or it can be a saddle. But in 3 dimensions, so in other words, we'll make analogies with 2-dimensional surfaces, but you really need to think of a curved 3-dimensional surface. So the universe can be flat, in which case it's what your intuition can picture is just infinite in all directions and just has Euclidean geometry everywhere. But it can also be a 3-sphere, which has finite volume, and could be pictured as a sphere embedded in 4 dimensions. The set of points in 4 dimensions, the surface in 4 dimensions, where every point is equidistant from the point at the center, which isn't part of that surface. So in this case, if you embedded it in higher reality, the 3-sphere universe would have a center, but it's not in the universe itself. It's not part of the universe. Or it could be a saddle, but it has to be a saddle that is infinite in size and a constant negative curvature. And crazily enough, well, any saddle you can picture in 3 dimensions has variable curvature. It doesn't have constant curvature everywhere. To make a 2-dimensional, negatively curved, saddle-shaped surface where the curvature is constant everywhere, you need to embed that 2-dimensional surface in 4 dimensions. And the saddle-shaped universe that's 3-dimensional, you couldn't even embed it in 4 dimensions. You'd have to embed it in 5 dimensions. So even if I got my 4-dimensional visualization, it'd be, damn it, in terms of, but anyway, yes?
When you say saddle, you mean like this shape?
I do, yeah, right. I mean a saddle. Hey, turn it to the camera. Look at that. It's a saddle. That's what I mean, yeah. So a 2-dimensional sphere has positive curvature. If you drew perpendicular lines to any point on the surface, they both bend in the same direction. The saddle has negative curvature because if you do that, the coordinate lines, so to speak, bend in opposite directions. For a 3-dimensional surface, if it's positive curvature, all 3 of them bend in the same direction. If it's negative curvature, 2 bend in one direction and the third one bends in the opposite direction, so to speak. Okay? So, let's list the possibilities. Let's start with flat, which appears to be the actual shape that the universe does have, at least the region that we can see. Flat, if kappa equals 0, Right, so one possibility is flat if kappa equals 0. That would be the curvature constant being 0. The metric is that of special relativity. That's our special relativity. In other words, it's ds squared is equal to c squared dt squared. So do you remember, the rest of it, if we don't account for the scale factor, would just be the metric of space, Euclidean geometry, written, we'll use spherical polar coordinates. I could use dx squared, dy squared, dz squared, but it's more convenient to use spherical polar coordinates. So I'll see if you remember, I'll write the first one. Dr squared plus, so in other words, dl squared, distance squared between two nearby points in ordinary Euclidean space written in spherical coordinates is dr squared plus, what's the theta piece? Not dr, we already got that piece. RD theta over squared because it's Pythagorean theorem, right? So plus r squared d theta squared plus, what do I multiply d phi squared by? It's not just r squared, I have to multiply by sine squared theta, right? Sine squared theta d phi squared. So here, we need to doctor this up with the scale factor. A squared of t times dr squared plus r squared d theta squared plus r squared sine squared theta d phi squared. Representing the fact that the universe is expanding. So these are co-moving coordinates. These are co-moving coordinates. That you have to multiply by the scale factor in order to turn it into, for our actual distances. Theta is angles, so that's different. Theta if you're angles. So now we do our usual thing, setting some of those differentials to 0. Setting dt equals d theta equals d phi. All of those are equal to 0, so I'm considering events in space-time that only differ in their radial coordinate. They're at the same time and have the same values of theta and phi. So in other words, we're talking about coordinates that are just along a radial line from the origin, whose location is arbitrary, but we say, we're at the origin. We'll set up these coordinates relative to us at the origin. We see that, so if I do that, dt is 0, d theta and d phi are 0, is ds squared positive or negative? It's negative. So does that mean is ds squared representing a proper time or a proper distance?
Distance?
Proper distance. ds squared is negative, means square root of minus ds squared is proper distance. So we see that a of t times dr is the proper distance along a radial line from the origin. Again, we know this because ds squared is less than 0 for events whose coordinates only differ by r. So the total proper distance, the actual at this time distance from you, the total proper distance to a point with radial coordinate r, is, well, I gotta add it up. So here's U. At 0, 0, 0. At the origin, there's some galaxy, a little spiral there, some galaxy that is at some r theta phi, so off in some direction specified by theta and phi. D sub b is the proper distance between you and that galaxy at whatever time it is. When do you think we would set the time equal to 0? At the Big Bang, we make t equal 0 at the Big Bang. So there's that galaxy. How far away is it at time t? Well, dt as a function of time will be add up from 0 to r all the little increments of proper distance a of t dr. And I'll be a good mathematical citizen and call it r prime in the integration. But I'm doing this at some particular moment. So can I pull a of t from the integral because I'm doing this at some particular fixed moment in time t? Yes, because I'm integrating over r, not t. So I can pull a of t out. A of t times the integral from 0 to r of dr prime. Quick! What's the integral from 0 to r of dr prime? It's just r, right? Because integrate r prime, you get integrate dr prime, you get r prime, and then I put in r and I put in 0 and subtract. It's just r. So this is a as a function of time times r. Thus, r in the metric here represents proper distance from the origin at the moment when we define a to be 1, which we typically take to be now. So r represents, little r represents current proper distance. How far are galaxies away from us now as their r coordinate? Because we're at the origin, because we're special. There you go. I was like, what are they sneakering? Yeah. Yes. Thus, r equals proper distance from the origin when a equals 1. And we usually take that to be now. So r represents how far stuff is from us now. And in fact, we use a 0 subscript to represent now. to represent, I'll say to denote present values. So we say that A naught, which is A at time t naught now, is equal to 1. We just say it. Could have made it any time. If we were weird, we could set A of t to be 1 5 billion years ago, and then A of t isn't 1 now. Well, why would we do that? That would be like saying, well, let's use Jupiter as the basis of Kepler's third law, right? Silly people. So we just do that. Question? No? Okay. Any questions? Because we're special. It's all about us. Okay, now let's do spherical and make ourselves sad, and we can't picture in 4 dimensions, because I'll make myself sad. But it's still glorious to be able to reason by analogy and say the words that a 4-dimensional creature would say, oh yeah, I'm picturing that. Lucky petard, I don't know. So, our universe will be, it turns out, spherical if the curvature constant kappa is greater than 0. The metric is that of an expanding 3-sphere. So it looks like this. S squared is c squared dt squared minus a of t squared times dr squared plus r naught squared sine squared little r over r naught times d theta squared plus sine squared theta d phi squared. And again, by the way, as has been the case in the past, things like d theta squared doesn't mean the differential of theta squared, it means d theta times d theta. Okay? Oh, I gotta close that parenthesis. Yeah. Spherical. What's the problem? Yes. Yeah. It's a spherical. Yeah, there we go. Not accurate. Okay, spherical. Spherical in that case, but it's a 3-sphere. It's a sphere that is 3-dimensional. It's a surface that is 3-dimensional, 0 thickness perpendicular to it. You need to embed in a higher dimensionality in order to visualize it, although it doesn't have to be, right? In other words, picture a 2-sphere, a sphere with a 2-dimensional surface. That's the sphere we're used to, and I mean just the surface, not what's inside, not what's outside. Okay, this is another thing where I can say the words and I can't make it happen in my brain, but imagine a spherical surface, and now eliminate the space inside and outside so that the sphere is all that there is. I can't, my brain needs it to be embedded in 3 dimensions, but logically it doesn't need to be. And a 3-sphere universe logically doesn't need to have anything inside or outside of it. It would just be, it's all that there is. And that's what we'd be potentially talking about here. Although, in principle, it could be embedded in a higher dimensional space. And string theorists like to have fun imagining such things. Now, whether they're just smoking the good stuff or not is another question, but in any case, let's take a step back to see what's going on here. By writing the metric on a two-sphere in analogous coordinates that you'll joyfully use, by the way, in the homework that I just posted due next Wednesday. So you get to think about this. The last homework would be the one where then you have to, so this is the metric on a three-sphere. In the last homework, one of the things you forget to do, I mentioned before, is figure out how to write the metric on a four-sphere. And from that, you can figure out how to write the metric on any sphere, no matter how many dimensions. But anyway, that's for later. In analogous coordinates, hold on to your head, because it might explode. I mean, not to a two-sphere when you're trying to think about it. Generalizing to a three-sphere. And again, I do love this stuff. I also wish I could genuinely picture it instead of reasoning by analogy. But oh well. So let's draw a two-sphere. And we imagine we're sitting at the origin. Now the outer location. And we'll think of it as being like the north pole of the sphere. Santa's workshop. Our location in Santa's workshop, because why not? On the north pole. There we are, okay. Some other point. Little r represents distance along the surface of the sphere, because we live on the sphere. We're two-dimensional creatures who live in a spherical universe, but it's two-dimensional spherical universe. The only thing we can do is move on the surface of the sphere. We can't even picture inside or outside of the sphere. And so we talk about distances along the surface of the sphere. That's what we measure. Does that make sense? R is distance along the surface of the sphere. So R equals distance along sphere surface from the origin. Our location, we always put ourselves at the origin. And if we do imagine this embedded in a higher dimensional, three-dimensional embedding space, well then we could say, okay, there's the center of the sphere, not part of the sphere, because it's not on the surface of the sphere anywhere. There's the angle theta, the usual theta of spherical coordinates. And we could imagine drawing a circle of constant value of theta on the surface of the sphere. And here is how far this point is from the axis of the sphere that we draw from the center in the higher dimensional space through our location. And here is the radius of the sphere in the higher dimension that we, living on the sphere, can't access. But we can still talk about the radius of curvature of the sphere, capital R. It's something we can measure by making measurements on our sphere. What's this distance right here? This is R, this is theta, so this is R sine theta, right? So I could call it R sine theta. There's R sine theta. But note that theta is little r over big R, because that's how angle is defined, right? Arc length that is on a circle divided by the radius of the circle is the angle. That's the definition of angle. Note that theta is little r over big R. So R sine theta, what we might call the actual radius of that circle of latitude that I drew on there. Can be written as R times the sine of little r over big R. Okay, so this is analogously doing something in 4 dimensions, if you will. Metric on sphere, it'll be dl squared, squared the distance between unified points. Well, there will be a part that's just dr squared. If I go this way, if I keep going in the direction r, dr is how far I went. So there will be a piece that's just dr squared for motion only along r. But the other piece is I move in this direction along the circle of latitude, perpendicular to motion just along r. And it's the usual thing, right? Because we've done this before, just in different notation. So, in a sense, so in spherical coordinates, here's r sine theta. So if I move in the phi direction, I'm moving along a circle of radius r sine theta, an angle d phi. What's that distance? Right? Here's the origin on the surface of the sphere here, dr. So now I go d phi at radius r sine theta. So this is r sine theta d phi. R sine theta d phi. So the metric is dr squared plus, it's the big R, because it's the whole radius of the sphere there, r squared sine squared theta d phi squared. But instead of using theta, we're using little r over big R, which is theta, but creatures on the sphere can't see theta, but they can measure little r, and they could know what big R was from other measurements they made. And so in other words, we say that it's the r squared plus r squared sine squared little r over big R times d phi squared. I'm sorry. Yeah, okay, now we gotta be careful, But it gets, right, here's this other one too, okay, so here's the problem. But if we just stick with this piece, let theta be this role here. Okay? Now, so there's a lot of similarity there on our two sphere. When we go to the 3 sphere, we got the sine squared theta here, is the ordinary polar angle in polar coordinates. What this represents for the 3 sphere is a new angle that we'll call chi, like chi, whatever you want to call it, that is building up our 3 sphere by stacking 2 spheres. So we're basically almost out of time, so I'll just describe right now and we'll complete next time. But I want to have at least said this before we go. All right? So, this circle can be called a 1 sphere. We use the word sphere to just generically represent the idea of circles or spheres in any dimension. So a 1 sphere is a one-dimensional sphere. In other words, its surface, if you will, is just one-dimensional, right? Only move in one direction on it. A 0 sphere would just be 2 points. 0 dimensions, 2 points, same distance from a point at the center. A 1 sphere, you can put into 2 dimensions. It's a bunch of points that are the same distance from a point at the center. This is a 1 sphere. The 2-dimensional, what I normally think of as a sphere, this is called a 2 sphere. Its surface is 2-dimensional. And I can think of it like this. I can make a 2 sphere by stacking a bunch of 1 spheres together whose radii vary as you move along the stacking axis, defined by the radii are r sine theta, where theta is this polar angle away from this axis right here. So I stack a bunch of 1 spheres in just the right way, make their radii vary in just the right way, described by this angle theta, this polar angle. And when I'm done, I've got my 2 sphere. Now, they're stacked along this axis. Does the axis pass through any of the 1 spheres? Does it actually penetrate any of the 1 spheres? No, it goes through their centers. It doesn't touch them, right? So, how do I make a 3 sphere? Why, it's simple. What I do is, I take a bunch of 2 spheres, and I stack them along a direction perpendicular to every direction in our space. Along a 4th dimension, I stack them, and they're described by this polar angle, polar angle chi, r over r, chi, and so I stack them, and they're stacked along this axis that passes through all their centers, and because I've got enough room in 4 dimensions, the axis doesn't pass through any of their surfaces. And on here, every 1 sphere, you can describe it as distance along the 1 sphere itself is this piece right here. For our 3 sphere, every 2 sphere has its normal metric. Here's angle away from the z-axis on each of the 2 spheres. And this is angle away from the w-axis, that 4th direction that we can't visualize because it's perpendicular to our space. This angle, chi, is another polar angle. And ta-da, there it is. So blow your mind trying to think about all that, and later you'll get that homework problem where it's, okay, so to make a 4-sphere, you gotta make another stack, this time of 3 spheres, along a 5th axis with another polar angle, and you can see how it generalizes and make any kind of 3D higher dimensional sphere that you want. Ooh, all right, go forth and visualize in higher dimensions. Yay! Woo! Ooh, it's almost like monster truck rally. We're gonna turn the floor of the Coliseum into a giant blood pit.
Remember that, dear? Yes.